Good evening. My name is Shreyas Jayakumar, and we are part of team. I'm part of team three, and in collaboration with team four. And this is the demo video pertaining to our final project, W533. And as you can see from our screen, the topic is in-network computing for real-time multi-sensor health analytics. And uh, this is the entire team. The six members is roles and responsibilities. As you can see from our screen, Hobo Yang is the overall technical leader, and wherein his primary responsibilities is being that of the system architect and risk manager, and myself, Shreyas Jayakumar, I'm the overall business lead. And when it comes to the technical side, my responsibilities is pertaining to the compiler development for the overall compiler stack, and also like the software bridge layer. Yukinli is in charge of the application slash benchmarking and the adoption strategist. Rohit is going to work on the architecture part, that is the custom hardware acceleration. And when it comes to the business side, his deliverable is pertaining to that of market intelligence research. Akshaya is working on the physical design, and pertaining to the business part, she is the technology visionary. And last is my team's team leader, Siddharth, and he is going to work on the architecture as well in accordance to the evaluation. And when it comes to the business side, he's the unit economics lead. So high level overview pertaining to the system architecture. So as you can see from our screen, there are three layers. So the sensor layer, wherein uh, it's it's the properties, as you can see from our screen, is it's non-intrusive, periodically transmitting nodes, and there isn't any sort of local compute there. And then comes the network and the integrated compute layer. And so here, as you can see, it's the entire ensemble is integrated between a CPU GPU compute system. And the main advantages of this is that bandwidth is better, and reduced latency. And then finally comes the ML and the action layer, wherein here, pertaining to each specific patient, we load the weights and the parameters accordingly. And then the classification and detection happens accordingly. And finally, the market application and strategic advantages is that the implementation is portable, and the rather the challenge is that there is a lot of cloud dependency involved in it, and our solution is we are doing edge inference, meaning pertaining to our local device itself, we are going to process and then in detail, my teammate Rohit will talk about all the market research that he has done from a business point of view. Thank you for now.
I'm Rohit, and coming to the business side of a project. So this week we have explored like who are the major players in this field, and how are they approaching the problem, and how our solution is better than this. So coming to market leaders, so there are like three major players in this segment. One is iRhythm, AliveCore, and Heartbeam. So so if you look at iRhythm and Heartbeam, so their approach is like cloud-based computation, which means they'll send all the data that's mounted by the sensor that's to the cloud, and in the cloud, required ML models or is run on the data, and the results is again fetched back to the devices. And coming to AliveCore, so they're using edge-based edge or IoT-based approach. That means each and every device has uh, its own compute. Uh, so the advantage of this approach is it has better latency, but the downside to this is it consumes a lot of power. So coming to our solution, so it's in between. It's our approach is in between, like uh, both of this, and uh, it. So our approach is network-based computing. So where we have like one computer system for entire for all the sensors. That means each sensor is a node in the network, and we have a centralized compute system. So each node uh, will be energy efficient. That means its job is to only to uh, measure the uh, measure the data and send it to the network, and it need not do any computation. So this way we can have like uh, better battery life. And the other advantage is we can extend this we can extend this that means we can add like multiple sensors to our system, and we need not uh, and these sensors can be in any simple sensors, and we need not build a new IoT device in case of like extending or scaling up the system. So we can just update the software layers whenever we add a new sensor to our system. So that way, our system uh, uh, fills the gap that's there with the existing solutions. Yeah, this is what we have done for our market research.
One.
Data preparation and pre-processing part. So for the data set, this is a publicly available benchmark for ECG data set. And so it contains like ECG recordings from real patients, and they're like over a period of like 48 hours. And they are like, it has like annotations about the type of arrhythmia as well. So the data format like has like 3 files, which we are primarily going to use for the ML like for training the ML model. So it has the .dat file, which is the raw ECG signal in binary format, like the 2 and 2 format, and it also has like 2 channels. And .hea is the header file, which contains the metadata. So like the sampling rate, number of channels, and how to decode .dat. And ATR is the annotation file, and this talks about like this tells the like our peak locations, like the heartbeat positions and the beat types. So this will be used for like labeling the data during the training process. So this is the visualization of the ECG, raw ECG waveform that is present in the data set. So as you can see here, we have like timestamps running here, and you can see the ECG waveform here, and we have like 2 channels here, ML2 and V5, and this is the ATR, like the annotation, defining the peaks, R peaks, and the shape. So first, in order to so the data set that we have like it contains a lot of information. So in order to train the ML model using the data that we have, first we need to prepare the data for training. So what we'll be doing is we will take the actual WFDP records and then convert them into like NumPy data set. Which is like available to train the like ready for training the model. So we'll also be like segmenting the data into shorter periods, and if there is if it's not a pixel length, we'll be using zero padding and to handle the edge cases. So after processing, the data will be saved into a .npc file. I'll be showing the processing here. So this is first the visualization of the data. So I'm taking a like one sample. So I'm going to show you the one of the sample. This is the one of the beats in the data. So this is the preparation part where we'll be parsing it. Like we have like default beat symbols. So we'll be passing the data, and then we're going to have like this tuple for different fields of the data. These will be presented in the output. So if I run this, we can see that it's taking out the passing the number of segments and the normal number of heartbeats and the abnormal number of heartbeats. So the output is stored here as this file. So this is the .mpc file, that is the output. So the output format is like this. So it contains the various fields in the data set. We have extracted this in order to train the model. In the next part, we have the data pre-processing part, where we have the raw data here. So we'll be normalizing that data and we'll be center cropping the longest signal and like zero padding it. So in this part, we'll also be splitting the data set into training, validation, and testing data set. And we'll have, at the end, we'll have a ready-to-use NumPy array for training and inference. So, we are pre-processing the data. So we have like resize signals. So this will be resizing the signals, like segmenting it. And then we'll be normalizing it. And also we are assigning the binary labels like 0 and 1 for normal and abnormal. Yes. Thank you.
So one of the crucial things for us in terms of hardware implementation of ML is quantization and pruning. So I'll go ahead on what's quantization pruning and how we are implementing it in our design. So pruning is a method for removing unimportant parameters from the deep learning model to reduce model size and improve the model. So we have to remove some not important weights so that which don't have much impact on our accuracy for the final output. This is kind of crucial because of our lack of memory space and number of computation we want to have in our model. Like our memory space around 2 kilobytes at 64-bit. So we don't want to load something which is any like weight which is kind of exceeding the 2 kilobyte and also having enough space for other operations. So we have to like concise our memory. So we have to reduce the number of weights we need. So for this, you have to like remove a couple of weights which are not important for the ML process. So this is actually, we are determining this in two types. We can determine training time pruning or post-training time pruning. So during training time pruning, you just assess what are in like when doing in your training in computer, we just assess all the neurons and weight which can be shared without disrupting the final outcome of the model. So we can remove some and then like train and more, train and go, at every step we'll train more and remove some of the unimportant like weights, which would have like just a very like 0.001 effect in our accuracy. So which we can remove. And similarly, after post training also we can again look at some weights which are like not having much impact on our model and like try to remove those weights. So and then we had to reduce with the reduced amount of weights we had to load it into our hardware and then into the data man for our hardware for testing and testing system in the ML algorithm in our hardware system. This way we are going to compress the weight into sufficient enough for our hardware specs, and also it's also going to have a very lesser computation time for our model, and which is kind of crucial in terms of edge computation. So other step we can do is quantization. So quantization removes the precision model parameters, which lead to faster calculation and reduces the model size as well. So in this, we are going to change the data type structure. From example, if it's like brief float 32, we want to reduce something which is more tangible for us in our processing system. So for, our processing system are built more towards bfloat 16 and in32 operations, based operations with our ALU and programming element and tensor code specifically programmed for those operations. So in those operations systems, we can't load like any beep float 32 data or something higher specs, especially weights, because we won't be able to compute anything with it. So we have translated into something which is more suitable to our format, which is like again bfloat 16 or in 32. so that we can do some computations for that. So this reducing number of bits also is going to affect our memory as well as as the amount of data required will be less, and more as we have only like a total of 64 bit with data bit, we have to concise it into that space and make operations with that. So we have to do like based upon the parameters and weights we're getting, we have to like reduce in more shorter formats to make it more concise for our model. So that is what we are trying to do. Yeah.
Okay. Shreyas Jayakumar here again. So from the technical perspective, as I said last week, after having for now decided the ISA that we are proceeding with for both the CPU and GPU, I started researching on the compiler and the kernel development. And as you can, I have started documenting everything over here. And it's a detailed compiler stack. So basically, we first have from a high level point of view, we have like a CPU assembler, and then comes the GPU assembler after the CPU is being thoroughly validated. And then the third phase will be a driver / an API layer. And then the fourth part will be like demo program and nodes. And finally, in the end, we'll have like all the performance related calculations, in particular pertaining to all those metrics related to latency, either by checking for static scheduling and by employing Amdahl's and Gustafson's law, if we can see like what portion of the code can be parallelized and etc. So, but the key part is the first part, as you can see, is to proceed with the CPU assembler. And the programming language that I went with is Python. Initially, after having researched quite a bit, I thought that the best way would be to go with C. But given the fact that we only have a small set of instructions, from a latency point of view, we would only save a couple of milliseconds, and C becomes extremely useful only in the case of when we have to do compilation for an entire Linux kernel. So in that way, like GCC or LLVM and all swear by C, because there are like millions and millions of instructions over there. But for our student project, I think it would be best to proceed with Python, because when we have to come up with all the helper functions, and any sort of basically parsing, coming up with the lookup tables, by employing dicts, either as a dictionaries, that is as a key value pair, and etc. These are all native when it comes to Python. And not only that, as we know, debugging is also extremely fast. And so because of a multitude of reasons like this, we decided to go with Python. And now, as you can see, I'm going to talk about the implementation pertaining to the CPU assembler. And inside the CPU assembler, there are a multitude of components pertaining to starting with the tokenizer or the parser, and then comes a symbol table and encoders for the different types of instructions that is present. R type, meaning arithmetic, and the immediate instructions pertaining to that, memory instructions, LDR, STR, the conditional and unconditional control flow statements, that is branch. And at the moment, we have only 0 extended, and therefore there is only forward branches supported. And no ops are being because of the fact that we haven't implemented any sort of forwarding and hazard detection logic. When it comes to no ops, we have to manually insert. And it's a 5-stage pipeline. So the safest is 3, but for now, I have decided to proceed with 3. But then when it comes to calculations of performance, then I just have to make sure that if 3 is absolutely needed in case of all raw hazards, because if not, then it will unnecessarily increase the IC, and thereby ET will also reduce, which thereby directly or indirectly impacts the performance. So like slightly talking about like the subcomponents in a bit detail that is pertaining to like the tokenizer and etc. So what I have thought about is like so the different sections that we need to have is, as I said, first comes with the lookup table. So basically, like based on the condition type, the condition codes and the opcodes that we have implemented in our Verilog file by just having a like a two-string key, and the value will be like a 4-bit code accordingly. And then the second section would be like the related helper functions. Basically, like here, meaning like we have to like in for the registers and the immediates, it's direct. But when it comes to like parsing an entire mnemonic, for example, like an instruction like add C, we just have to like split it. Like there might be a single instruction with two sub instructions in that, and accordingly we need to like split it and proceed. And then comes the encoders, which I talked about earlier, like for R type, for immediate type, for memory instructions, branch, and of course, the hard-coded no-op instructions. And then comes the dispatcher instructions, the dispatcher-related module, wherein like here what happens is um, like each instruction is being routed to the right encoder based on what the base mnemonic is. And then finally, like the fifth section is like we need for now we have decided to directly write the COE file into our IMEM. And yeah, so that's like a high level explanation of how I have started proceeding with the implementation of the assembler Python script. And yeah, just gonna I've started with section 1, that is the lookup tables implementation, and have started going to section 2. So all these are based on the design that we followed with. And so starting with the condition codes, the different condition codes, and then comes the opcode table. And then because of the fact that for our CPU we are following the official ARM 70 DMI ISA, we have flags. And these four instructions, as we know, in accordance with the ARM 70 DMI ISA, the set bit always has to be 1, and there is no destination register for this. And then yeah, so basically I just all the mnemonics are being present in a sorted order here. And yeah, the from 11 through 15, as we know, in accordance with ARM 70 DMI ISA, are all fixed for like they are all like fixed registers, and they're SP being the stack pointer register number 13, LR is the link register, which is used in case of jump and link, and 15 is for the program counter. So as you can see, this is the second part, which is the helper and the utility functions. And as I said, so this is the parse register function. And accordingly, it is followed with the parse immediate helper function, and then it will be the parse mnemonic function, which I'm yet to implement. So the goals for next week's video for me is to completely finish off the CPU assembler part in entirety, and also like encode known instructions, that is verify it by hand, and then proceed with the testing part, and then get started with the GPU assembler, because CPU assembler is pivotal. And yeah, we need to get that working, and yeah, and then move on to the GPU assembler. So thank you.
Okay, thank you, Akshaya, Stas, Rohit, Shreyas, and this is Hobble. I'm going to show you what we did to implement our network, our NetFPGA. So, okay, so actually we did reprogram the GPU and also the CPU. We are using the new GPU ISA, WRP, and RDF to read and write the parameter to the GPU, and also the GPU already have the ability to get the start offset and the offset of our network payload so that we can directly gather memory range for those part data. And after we do the modification for those data, we send it up. And what innovation we did for that part is actually, so the original part, like the X data is started from the 0 at the DMEM to the 64, but now we want those ports come from the network, but we already have the payload. Sorry, so if we already got the payload, which means like the X don't not only take the 64 space, but add the headers. And we need to also put the width and the bias not started from the 64. So here we make it started from the 100. So like with 64 with 1 and 64 with 2, to bias, we get the end of the address at the 229. And the original way we do the calculation get the result is directly modify these two bias. But now we have the 230 and 231 to store for logits. So this logits will be changed once we get a new package. So which means like we can store these two bias here. And when we get a new package, we restart the GPU, we do the calculation again. So like this logits will also change. So like we can get the new logs every time. And since the logic for getting the package is we modify the range of the start offset and the offset end offset. So that which means like even though we get the logits which is result here, we cannot get it from another node which is receiving the package because we can only get the range from the start offset and the end offset, right? So now we have not only the inference GPU program, we also have another program to say like we clear the original X space. So like after we do the clear, the X, which is started from 0 to 64, will be set to 0. And also we put the logits, okay, is here, result right. So this loop is used for putting the result to the original X part so that we will say like the first line is a result and the second line is another result. And after that, it should be all 0. And this will all be shown inside the Yukun's representation. So let's handle this part to Yukun and let him to give us a representation about that part. And
Okay, as we can see, we already make the bit file and download it inside, and we are using this simple Python to download the smart NIC to write GPU instructions and write CPU instructions and write the parameters inside the memory from the address 100 and after we do all the reset, we could find that we could send a packet. This is containing all the datas. Wait a minute. Yeah, we could try like this. This is some real datas for ECG signals and this is our target port that is listened to. Yeah, it's listened to the code and we send the original data and we'll find that from the TCP dump that the result is correctly as we test on the software, and we could check the file. Yeah, we could check the file that all is 0 except the origin to 1, the first to 1. And this is the calculation of our GPU. And that's our hardware implement. Thank you.